Hello, I'm Richard Jacob from Matrix Science. Modifications are an important aspect of database searching. This talk describes how we handle both natural, post-translational modifications and also chemical modifications, which may be deliberate derivatization or accidental artifacts of sample handling. Modifications are a very important topic in database searching. In some cases, the main focus of a study is to characterize post-translational modifications, which may have biological significance. Phosphorylation would be a good example. In other cases, the modification may not be of interest in itself, but you need to allow for it in order to get a match. Oxidation during sample preparation would be an example. And of course, many methods of quantitation involve modifications containing isotopic labels. Some sequence variants, such as a substitution of one residue by another, are equivalent to modifications and can be handled in a similar way. Comprehensive and accurate information about post-translational and chemical modifications is an essential factor in the success of protein identification. In Mascot, we take our list of modifications from Unimod, which is an online modifications database. There are other lists of modifications on the web, like delta mass on the ABRF website and ResID from the EBI, but none is as comprehensive as Unimod. Mass values are calculated from empirical chemical formulae, eliminating the most common source of error. Specificities can be defined in ways that are useful in database searching, and there is the option to enter mass spec specific data such as neutral loss information. This screenshot shows one of the better annotated entries. I can't pretend that all of them are this detailed. Nevertheless, it is a very useful public domain resource that beats having to create your own list in an Excel spreadsheet or on the back of an envelope. If you go to the help page, there is a link to download the contents of Unimod as a Mascot modifications file. This is the easiest way to keep the modifications list on an in-house Mascot server up to date. Here's a tip for you. The default list of modifications displayed in the Mascot search form is a shortlist, containing only the most common mods. If you want to see the complete list of mods, and you are using Mascot 2.2 or earlier, you need to follow the link at the bottom of the search form selection page. Check the box for Show All Mods, then choose Save. This still sets the default state of the checkbox in Mascot 2.3, but we decided to place the checkbox on the search form so as to make it easier to swap between the short and long lists. It is extremely important that you do not choose more than the absolute minimum number of variable modifications in a search. We talked about this in an earlier presentation, but it is worth repeating. Variable or differential or non-quantitative modifications are expensive in the sense that they increase the time taken for a search and reduce its specificity. This is because the software has to permute out all the possible arrangements of modified and unmodified residues that fit to the peptide molecular mass. As more and more modifications are considered, the number of combinations and permutations increases geometrically, the so-called combinatorial explosion. Some variable modifications are worse than others. Modifications that only apply to a terminus, especially if they only apply when a particular residue is at the terminus, like pyroglue, make little difference to the number of peptides to be tested. The problem modifications are the ones that apply to residues in any position, especially if they apply to multiple residues, like phosphorylation. Unless you have enriched the sample in a particular post-translational modification, e.g. IMAC for phosphopeptides, it is usually not a good idea to try and catch post-translational mods in a first-pass search. Better to use a second-pass search, which we call an error-tolerant search, to catch the low abundance mods. We will come back to this later. To illustrate this point, this search of a single MS/MS spectrum using one variable mod gives a nice, statistically significant match. If the search is repeated with 8 mods, the match is the same with an identical score, but now it is barely significant. All of these mods have effectively increased the size of the database by a factor of 30. What's worse, the search takes over 10 times as long. So, use variable mods sparingly, you'll get better results and faster. By the way, the yellow region in the histogram indicates scores above the homology but below the identity thresholds. You will only see these regions highlighted in an MS/MS search report if it is a search of a single spectrum. Of all post-translational modifications, phosphorylation is one of the most interesting and also one of the most difficult. Why is it such a challenge? You have to contend with site heterogeneity, poor ionization efficiency, 3 fragmentation channels. There's the intact fragments, neutral loss of 80 Daltons, and neutral loss of 98 Daltons, and it can occur at serine, threonine, and tyrosine, which is equal to approximately 16% of the residues. Let's look at an example or two. One of the most common phosphopeptides comes from the milk protein beta-casein. There are 2 potential phosphorylation sites, serine and threonine, but only one is modified. Because the 2 sites are widely separated, the 2 arrangements get very different scores. Beautiful spectrum, long run of Y ions. Move the phosphorylation site to threonine 9 and many matches would disappear. Mascot 2.4 reports site localization probabilities using the delta score method published in Molecular Cellular Proteomics by Bernard Kuster's group. They analyzed a collection of synthetic analogues of real phosphopeptides and determined what score difference was required to determine the correct site with an error rate of, say, 5%. Because we don't expect anyone to calibrate their data in this way, we have made the calculation slightly more conservative. A score difference of 10 would give approximately 90% probability that the higher scoring arrangement was correct. A very large score difference, such as the one we were just looking at, gives a 100% likelihood that the phosphate is on serine 3. However, casein peptides are unusually easy to analyze. Here is a more typical example of what you can expect to find: a strong match to a phosphopeptide from a protein kinase. There is little to choose in terms of score between having the phosphate on threonine 1 or threonine 3. We can see why there is little difference in score between placing the phosphate on threonine 1 or threonine 3. There is just one extra match peak, and in probability terms, there isn't a huge difference between 20 matches using 55 experimental peaks and 21. However, if you had to choose one or the other, you'd probably go for threonine 1. The delta score site analysis suggests 70% probability on threonine 1 and 30% on threonine 3, much less clear-cut. We can't be confident which site is modified or whether there is a mixture of both isoforms, but we can be confident it is not on T7, threonine 7, or tyrosine 10, because the score drops dramatically, and these are assigned 0% probability. Sometimes it is worth looking at the sequence annotations to see whether these are known phosphorylation sites. If the database sequence doesn't have detailed annotations, you can follow the BLAST link to try and match the peptide to an entry from a better annotated database. In this case, we're searching SwissProt, so we can go straight to the Protein View report. According to SwissProt, both threonine 1 and threonine 3 are possible phosphorylation sites. If you really need to know which was the case here, or whether it was a mixture, you'd have to acquire more data. Maybe try a different enzyme, or target the incomplete cleavage peptide that includes the preceding lysine and glycine, so as to move the sites towards the center of the peptide, where you might get stronger B and Y fragments. If you are using Mascot 2.3 or earlier, the delta score calculation is not performed in Peptide View. These are our suggested guidelines when using Mascot for site analysis. If alternative sites differ by 20 in score, safe-ish to disregard the lower ones. If alternative sites have similar scores, you may be able to choose one by inspection, but be careful, one peak is just one peak. Often, you just can't differentiate between adjacent sites, even with great data. Now, back to the challenge of finding post-translational modifications. There are many hundreds of modifications in Unimod, yet I've emphasized the importance of using the minimum number of variable modifications in a search. So, how are we supposed to find unusual modifications? If you are searching uninterpreted MSMS data, the efficient way to find unusual modifications, as well as variations in the primary sequence, is a two-pass search. The first pass search is a simple search of the entire database with minimal modifications. The protein hits found in the first pass search are then selected for an exhaustive second pass search. During this second pass search, we can look for all the possible modifications, sequence variants, and non-specific cleavage products. Because only a handful of entries are being searched, search time is not an issue. It would be extremely difficult to calculate meaningful statistics from the additional matches in an error-tolerant search, and we don't report expect values. The evidence for the presence of any particular protein are the matches from the first pass search. The additional matches from the second pass search serve to increase coverage and may discover interesting modifications or single nucleotide polymorphisms, SNPs. For modifications, an error-tolerant search looks for one unsuspected modification per peptide in addition to those mods specified as fixed or variable. This is sufficient because it would be rare to get two unsuspected mods on a single peptide. The error-tolerant search looks for sequence variants such as a single nucleotide polymorphism, SNP, or sequence errors. For a protein database, we can't look for the consequences of inserted or deleted bases because these give rise to frame shifts and the entire sequence changes from that point on. There are some constraints on the standard first-pass search. Enzyme must be fully specific. A reduced ceiling on the number of variable modifications. Default is 2, but this can be changed globally in mascot.dat or for a user group in mascot security. It cannot be combined with an automatic decoy database search. It cannot be combined with quantitation. The search cannot include error-tolerant sequence tags. Otherwise, submitting the search is just like submitting a standard search, except that you check the error-tolerant checkbox. And here is the first hit of the result report. The additional matches found in the error-tolerant search are the ones without expect values. One of these, query 133, is a simple, non-specific peptide with a very good score. There's another example for query 176. The error-tolerant search is a much better way of picking up non-specific peptides than searching the entire database with semitrypsin or no enzyme. We only fail to get such matches in an error-tolerant search if there are no matches to the protein in the first pass search. However, you have to ask yourself whether you would believe a protein hit in which the only peptide match was non-specific. I think the answer is no. The matches from an error-tolerant search are aggressively filtered to remove junk matches. An individual peptide can be semi-specific or have one unsuspected modification or have one primary sequence mutation. If the mass delta of the modification is less than the smaller of the precursor mass tolerance and the fragment mass tolerance, the modification is rejected. This eliminates modifications that are meaningless given the estimated mass error, like glutamine to lysine in most cases. The match must have a score of at least the identity threshold for the same query in the first pass search. The match must have a score in excess of the highest scoring match to the same query in the first pass search. Take a look at the match to query 136. The mass tolerance for this search was fairly wide, so the observed mass difference could correspond to either carbatoidomethylation or carboxymethylation at the N-terminus. Since this sample was alkylated with idoacetamide, we would choose carbatoidomethylation as the most likely suspect, especially as this brings the error on the precursor mass into line with the general trend, whereas carboxymethylation would give an error of plus 0.6 Daltons. The assignment to carbatoidomethylation is also very believable, because this is a known artifact of over-alkylation. The same modification can be seen in this screenshot for 3 other queries. Another easily believable assignment is pyroglue for the match to query 252. As is methylation for threonine 8 of query 211. In other cases, the match may be good, but the assignment is not believable. Query 145 is listed with a substitution at phenylalanine 8, causing a loss of 48 Daltons. This seems unlikely because we have 2 other matches to the same peptide without any substitution. What else could it be? Well, notice that the 2 other matches are both oxidized at methionine 7. If we suppose this peptide is also oxidized, then the mass shift becomes minus 64, which is a well-known loss for oxidized methionine, loss of methane sulfonic acid. This would seem a much more likely explanation for this match. It is important to understand that the error-tolerant search finds new matches by introducing mass shifts at different positions in the database sequence. The match may be very strong, but figuring out a credible assignment can require a bit of detective work. You should also look at the other matches to the same query when trying to decide whether to accept a match or not. In this search, acetyl N-terminal was a variable modification. The error-tolerant search got the highest score for this spectrum by including this modification at the same time, subtracting 42 Daltons at E5. Much more believable is to take the original match from the first pass search, which is a match to the unmodified peptide with a slightly lower score. In summary, an error-tolerant search can successfully locate mass differences corresponding to a single unsuspected modification or a single SNP per peptide. The user must decide on the best explanation for the observed differences. It is limited to proteins that have at least one good peptide match, so it's not very useful for, say, MHC peptides.